In the quest for knowledge, there are realms of understanding that beckon us to explore beyond the familiar. Among these is the captivating world of special theory of relativity, a cornerstone of modern physics that challenges our perceptions of space and time. In this video, you will embark on an odyssey of learning, charting the course through the best books, resources, and methods for studying special relativity. You will also come to know what is the mathematics that is required to study and how to get those resources from some very authentic sources. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this flash video on how to learn special theory of relativity. Our quest, our zeal to learn such remarkable scientific theory takes us back to those memorable lines which Tennyson wrote in his famous poem Ulysses. It little profits that an idle king by this still hearth among these barren crags, matched with an aged wife I meet and dole unequal laws unto a savage race, that hoard and sleep and feed and know not me. I cannot rest from travel, I will drink life to the lees. This last line, I cannot rest from travel, I will drink life to the lees, actually speaks of the positivism which Tennyson wrote in his poem Ulysses. The zest for life, the eagerness to know more and more, and that is why we are just like Ulysses, striving to learn more and drink life to the lees. For this takes us into our today's video where we are trying to explore and learn, and we cannot rest but learn what is special theory of relativity. So in this section of this video, I'm going to explore and tell you in quick short some of the very interesting facts about what is special theory of relativity coming up into the next part of our video. Now, if I take the general statement, it is called that the special theory is very a kind of a scientific theory which actually establishes a relation between space and time. Now, on June 30th, 1905, the German physics journal Annalen der Physik actually published a paper which you can see on the left-hand side. This is the upper cover, and it was done by a young patent clerk called Albert Einstein. The paper, which I won't dare to pronounce it in German, it is called On the Electrodynamics of Moving Bodies, set out Einstein's theory of special relativity, which actually explains the relationship between space and time, between energy and mass in the famous equation E equals to mc squared. Now, the paper actually uses Planck's concept of energy quanta to describe how light travels through space. And the first, I would say the two postulates, very important, that the laws of physics are invariant, identical in all inertial frames of reference. And the second postulate, which tells that the speed of light in vacuum is the same for all observers, regardless of the motion of light. Now, the first law or the first postulate was already established by Galileo Galilei many years back, and that is called the Galilean relativity, which I think you're quite aware and you know. Now, every scientific theory, including special theory of relativity, arises due to certain limitations. And as you can see that there is some kind of an incompatibility between certain two very classically established theories which led to the formulation of special theory of relativity. We call it incompatibility, some people call it limitations, but anyway, we need to understand that all scientific theories are correct and none of the scientific theories can be termed as wrong. Now, the incompatibility arose actually out of Maxwell's, I would say, laws of electromagnetism along with the incompatibility of Newtonian mechanics. Now, at this point, you might be wondering why we are trying to reconcile Newtonian mechanics with Maxwell. Well, we are not trying to reconcile, but all those things are actually laws of motion. But when Albert Einstein and the physicists tried to reconcile or try to redefine Newtonian mechanics in terms of Maxwell's equations, we find there is a kind of an incompatibility. Also, the Michelson-Morley experiment, which resulted to detect the Earth's, I would say, motion against what was hypothesized as luminiferous ether, actually led to the developments of further mathematical formulation, including Lorentz transformations. History accounts that even Maxwell assumed there is something which is called a luminiferous ether, and he framed the mathematical laws of electromagnetism considering ether. Well, that is a different part of the story. So the incompatibility in terms of motion with electromagnetism and Newtonian mechanics and luminiferous ether, along with the failure to detect ether, was done by Michelson-Morley experiment, which resulted into the development of special theory of relativity. Now, at this point, you might be wondering that we call special theory of relativity something which is all related to the speed of light. Now, the question that you might be having in your mind, that why we are considering the speed of light, why not the speed of an aeroplane, why not the speed of a truck or any other lesser, I would say, moving vehicles or objects which are traveling less than the speed of light? Well, the answer is, if we plot certain things which are traveling less than or almost equal to the speed of light, then it would fall under this quadrant. So objects which were moving, which are still moving less than the speed of light or something, were very well, I would say, guided by the Newtonian mechanics. The problem arose when Einstein tried to formulate are those things which are almost equal to or equaling, they are approaching the speed of light. The reason is that if we consider the speed of light, then we can take all the laws of motion at its highest speed. I repeat, it is at its highest speed. So the lower speeds are concerned, are already defined by Newtonian mechanics, which is on this part of the graph. If we consider the speed of light, which is extreme, then all the laws of motion around this universe will be well guided. And that is the reason special theory of relativity is related to the speed of light, because we now know that nothing can travel more than the speed of light. So any object which is traveling close to the speed of light, if we can formulate them, then we are done. The entire theory stands to be perfect. So that is the reason, as you can see, that the Minkowski space-time and new types of mathematics, and also the union of space and time into space-time, and there has been a lot of counterintuitive phenomena. So considering objects which are traveling close to or equal to the speed of light, we needed a new type of mathematics. There are a lot of counterintuitive phenomena which arose, and there was a need for uniting space and time, which was thought as separate in terms of Newtonian mechanics. So we can summarize telling that special relativity actually revises the previously established laws of mechanics to address scenarios encompassing all types of motion, means which are also approaching the speed of the light, known as relativistic velocities. So here you can understand quite well that why always we consider the speed of light, etc., in terms of defining the theory of relativity. The word Annus mirabilis, actually I would say it is a Latin word which means miracle year, and it actually happened in the year 1905. That is why it is called miraculous year of Albert Einstein. And it was during this time that he published 4 papers that Albert Einstein published in Allen and Durr Physics, which I have just shown you in a scientific journal. These 4 papers were major contributions to build the foundation of modern physics, and they revolutionized science's understanding to the fundamental concepts of space, time, and energy. Now, if you consider the first paper actually explained the photoelectric effect, which established the energy of the light quanta with this equation E equal to hf, and was the only specific discovery mentioned in the citation which awarded Einstein the Nobel Prize in 1921. The second paper, which was called Brownian motion, established this relation, which you can see it is called Einstein relation, and led reluctant physicists ultimately accept that there is something which is called atoms. The third one, which introduced Einstein's special theory of relativity, which we are studying, developed the principle of mass and energy. And the fourth one is basically a consequence of the special theory of relativity, developed the principle of mass energy equivalence expressed in the famous equation E equals to mc squared. Now, together with those 4 papers, along with quantum mechanics and Einstein's later theory, which I have made a lot of video, General Theory of Relativity, are the foundation of modern physics. Now, you see, right at this moment, what we can find is that special relativity brought a whole new perspective to physics, introducing revolutionary concepts that had not been considered before, this time. And here is a breakdown of some new key things that emerged. What are the key things that actually emerged, I would say, from the special theory of relativity? coming up into the next part of our video. The first thing that came across is time dilation, that times run slower for objects to motion relative to an observer. If you imagine two clocks, one zooming by you on a spaceship, another resting on the earth, according to you, the clock on the spaceship will tick slower. The second one is called length contraction, where objects appear shorter in the direction of the motion. So if you hold a yardstick parallel to a speeding car, it might appear shorter than a stationary yardstick. This is because the car's length is contracted to the direction and which it's moving. The second thing we found is relativity of simultaneity, that events that appear simultaneous to one observer can occur at different times for another in relative motion. And the next one was the mass energy equivalence, expressed by the famous E equals to mc square, showing that mass and energy are equivalent and can be converted into each other. Now, in order to take all this consideration, there has been a lot of development in terms of mathematics also. The first one was that we found something which is called a Minkowski space-time. There's a new kind of a transformation which revolutionized mathematics and physics as a whole, which is called Lorentz transformation, and we also got a new idea of relativistic kinematics. At this point of time, I hope those who are watching this video will be able to understand what is special theory of relativity, how it developed, what are the implications, and most importantly, just like Ulysses, we are trying to drink the life to the lees. Having said that, what strikes more to our mind is that taken all these things, it is fine. But the question is that why you will learn special theory of relativity? I mean to say, till Newtonian mechanics, things were fine. Is there any reason that you need to really learn special theory of relativity, or you can just skip those parts? Coming up into the next part of our video. Let us understand that when you are learning special theory of relativity, the first thing that you are doing is that this is the first step towards learning relativistic physics. Now, relativistic physics itself encompasses a wide area of physics. For example, this is the introduction to modern physics, because relativistic physics, relativistic quantum mechanics, relativistic cosmology, and it has got a lot of relativistic things. So when you are learning special theory of relativity, remember this is the first step and perhaps the easiest step in learning, formulating, conceiving ideas about relativistic physics. You will also understand what is called the GPS technology, and special relativity, because it is the first step towards relativistic physics, gives you a deeper, much deeper understanding of physics. Now, apart from that, there are certain things which nourishes and fertiles your brain also. First of all, designing thought experiment, which Einstein did, which is called Gedanken. The reason is that you really cannot see things which are moving close to the speed of light. So you have to close your eyes, you have to exercise your brain, you have to widen your thinking power, conceiving something, maybe a ball, maybe an object, and maybe yourself who is moving close to the speed of light. What happens if it accelerates, if it decelerates, if it travels equal to the speed of light? So this special theory of relativity actually designs your thought experiment and it widens your thinking power. Also, you will get an access to a lot of interdisciplinary correction. For example, quantum mechanics, which is relativistic in nature. For example, relativistic cosmology and many other things. So we can summarize from here that this is the first step towards learning relativistic physics, which opens up a huge area in terms of learning. It explores your thinking power because you really cannot perceive and see people around or things around which are traveling close to the speed of light. And this is the first time that you create thought experiments and you design the thought experiments and do the mathematics. Having said that, you now get a complete clear idea that the reason for learning special theory of relativity, you also need to understand that special theory of relativity is not only related to doing or getting good marks in mathematics or physics, it is also related to other branches of science. That means with this knowledge of special relativity, you can move and make your career into various other branches. What are those? Coming up into next part of the video. I was speaking to Professor Shantan Chaudhary, and you have seen the podcast also with Professor Soumitra Sengupta from the Indian Association of Cultivation of Science. These stalwart people always concentrate and doing research on what is called a relativistic cosmology. Yes, astrophysics is essential for the understanding and the behavior of light and particles in an extreme environments, and most importantly what is called relativistic quantum mechanics, because relativity is interwoven with quantum mechanics, the science of the very small. And later you will see with Richard P. Feynman coming up and formulating quantum electrodynamics, relativity and special relativity is the cornerstone and the key to understand. I hope this makes you clear that how you can connect special relativity to other branches of science, how it will improve your career, and how it will enhance your thinking power in order to progress your journey in the area of physics and mathematics. The first and foremost thing which comes into our mind is that what is the mathematics? How much level of mathematics? What are the difficulties that we need to learn? And what is the mathematics that you need to know in order to learn special theory of relativity? Coming up into the next part of the video, what mathematics do you need to know? Now here is something which I have divided, that it is like a pyramid. Now the good news is that special theory of relativity, the learning or the mathematical part, can be divided into three parts. Now if I consider that you are learning special theory of relativity just for a very basic level, I mean to say you just have to get a kind of a hangover, a kind of a hang on what the basic idea is, then you don't need to understand any level of mathematics. And I'm going to show you in this video that there is a very good book which actually explains the basic level excellent way. School level mathematics, basic algebra, trigonometry, basic mathematical operations is good enough to get a basic level understanding of special relativity. If you go to the intermediate level, I mean to say you want to understand a little bit better, then I would say you can just learn calculus, linear algebra, vector calculus, and a little bit of how coordinates transform. Don't worry how much of calculus, how much of linear algebra you need to know, I will cover up in this part of the video. And if you want a little bit know more about the advanced level, then you need to know these things. Why? Give me a minute to explain. The more advanced form of calculus allows for a more compact and elegant way to express the mathematical framework of relativity, especially Minkowski space-time tensor calculus. Special relativity can be formulated using the language of differential geometry, particularly in the context of Minkowski space-time. Concepts like manifold, matrix, etc. Relativistic, I would say electrodynamics, yes, applying the principles of special relativity to the study of electromagnetism lead to a deeper understanding. Complex analysis, yes, can be useful in special relativity, especially dealing with complex valued functions. And group theory has applications in special relativity, particularly in understanding the symmetries of space, time, etc. Now you might be wondering that do we need to understand the basic, the intermediate, advanced, all of them? I would say let us concentrate to the intermediate level, just a basic calculus and all those things. However, if you don't want to go too much into the rigor of mathematics, basic level is good enough to make you understand. The question that you have in your mind is that what are the books and how much of calculus, etc. I need to know. Let me explain you very easily. So if you just go through this book, which is called Calculus Made Easy by Sylvanus Thompson, and I have made a YouTube shorts coming up in a few days, you can procure this online stuff through gutenberg.org. It is free, licensed, and you can learn this. Very easy book, very simple book, gives you an excellent understanding of integral, differentiation, and partial differentiation. This book is good enough in order to make you understand about special relativity. You can go through extensively with Gilbert Stang's linear algebra. This is the key book to understand linear algebra. I would also recommend to go for Daniel Fleisch vectors and tensors. Now if you don't want to go to tensors, you can skip that, but the basic understanding of vector algebra, this book is excellent. I would also recommend you to go through Maxwell's equations, because Maxwell's equations are the key to understand relativistic parts. So special theory of relativity will come and hit you hard on Maxwell's equations. Again, Daniel Fleisch books is an absolutely excellent guide to understand Maxwell's equations. So having said these are the four books, these are the four content which is good enough in order to get you a very good understanding of special relativity. So you now know what is the mathematics that you need to know. Now the question is that what are the books? What are the best books, or what are the real books, I mean to say textbooks, which are required to learn special theory of relativity? Coming up into the next part of the video. I won't bother you with too much of overloading your choice. The first book which I would recommend is this one, A Primer of Special Relativity by P.L. Sardesai. Now you see this book, I would say it is not a very popular book in terms, but it is excellent, because you can see 79 to 80% it has given a 5-star in Amazon, and these are basically the reviews from different people which says that the book is absolutely great. I mean to say it is an absolutely easy understanding of special relativity. If I go through the content of the book, you will see that it started with pre-Einstein. That means it gives you an understanding of GT. No, not general theory of relativity. It is Galilean transformation. It deals a lot into the applications, and then as I showed you, it deals with ether, the myth, the truth, etc. Lorentz transformation and the consequences are dealt with. Then it goes into the real relativity, that is simultaneity, colloquiality, relativity theory of some optics, etc. And also this book contains a lot into 4 vectors, which is an absolute necessary to understand. You see, relativity and electromagnetism, I was telling that how the charge density, current density and all these things changes, and the invariance of Maxwell's equation, page number 162. This is the key to understand how special relativity and Maxwell's equations are related. So you can very well understand that that is the reason I told you need to understand special relativity and what is the best book that you do. Well, this book contains a good amount of clear, I would say, diagrams. As you can see, I've just given a few screenshots. These diagrams are clear. Not much of, I would say, complex mathematics are given, and just a basic knowledge of calculus, or not even that, would be good enough to understand this book. The mathematical calculations are also quite simple. As I have given you very simple examples, you can see here, hardly there is any calculus, and the trigonometry actually explains things well. So from my point of view, if I tell them this book is actually just contain the right content, it is actually containing the calculus and the basic mathematics, simple and right up to the point. It is neither too intuitive, that means all in a very lucid and a juicy story, and it is neither too mathematical in nature, and most importantly it contains a good amount of exercises, and this can lead into practice. Now this is, I would say, a kind of a book which will neither throw you into the rigor of mathematics nor give you an intuitive idea, but a very good understanding of special theory of relativity. The next book which I would like to recommend is a very basic book, a very popular book, that is called Space-Time Physics, and this is by Taylor and Wheeler. This is considered to be a very easy book, and I will tell you why. So those who are absolute beginners, those who really don't want to get into the mathematical rigor, this would be the good book for you. There are various other reviews which are spread across Amazon, and you can check it. The best, this is an amazing book. So I just given you a few screenshot to understand that this is really a wonderful book, and Archibald and Wheeler actually are one of the greatest, I would say, explanatory people who explain things quite easily. Coming back to the book content, you see this is a space-time overview which has been given. It is around 300 pages. So this book, gives you the content is a little bit unusual because it doesn't go through the convention, but this is the overall idea of the book. Now, the most important feature which attracted me for this book is that there are very detailed diagrams. These diagrams are excellent. Although this is a little bit hazy because I have taken screenshots, you can go through and it is very important. The mathematics is a little bit, I would say, different for those who are looking into deep into mathematics. But you see here that interval square is equals to space separation and all those things. So it actually doesn't uses even calculus. If I am not wrong, you can check into that. But uses the basic mathematics, basic arithmetic, basic algebra, and gives you a complete detailed understanding of this book. So this is a book for absolute beginner. You do not need to have any mathematical background, saving basic algebra and trigonometry, and the derivations are very simple. And this is by far, I would say, the best introductory book, which doesn't bother you, doesn't really make you feel complicated, but gives you a very thorough understanding of special theory of relativity. Coming to the next part, I would say that this book, which is a little bit more mathematical and very good in nature, that is Michael Samperle's Special Relativity, and this is Professor Samperle, Michael, University of Athens. And the top review more or less tells that the book is very good. Now this is a mathematical book in nature. Those who are really interested to know deep into the mathematics, I would definitely recommend to go ahead with the book. You see, the content of the book is very exhaustive. So it first gives you an idea of the mathematical part. So it deals with tensors, operation of tensors, Lorentz transformation. That means whatever the mathematics that you require later has been given up in this first 52 pages. Then the structure of the theories of physics, the role of physics has been given. Then it deals with Newtonian physics. Professor Michael gives you a complete idea of the fundamentals of special relativity, and most important feature is that also this book contains a lot about the four vector part. The relativistic kinematics is also being covered in details. Later you will see even the rigid motion and hyperbolic I would say motion, paradoxes, mass for momentum, relativistic relations, and you can see it ranges a lot. I think it is around almost 600 pages. So here you can see that the four force, irreducible decomposition. So this is a real rigorous understanding, a very simple yet a very true mathematical understanding of special relativity. If you tell my opinion, I would say this is the best book for medium and advanced learners. Yes, you need to know very well calculus, including PDEs, vectors and linear algebra. This book has a beautiful mathematical expositions. I have gone through it. It has got 500 problems. So those students who wants to learn and practice for your exam, this is a very good book. The mathematics explained clearly, and this is a remarkable book because it covers many aspects of special relativity with sound mathematical treatment. So this book is definitely for medium and advanced learners, and you need to have a understanding of mathematics. Coming to the last part of the third book is one of the best book, which I'll call of Leonard Susskind and Art Friedman's Special Relativity and Classical Field Theory. I have just given it is 82%. I won't wonder if it goes beyond 100% because I have read thoroughly this book. It is a wonderful book, and these are some of the reviews given. Remember, this book actually contains special relativity, but it also deals with something which is called a classical field theory. Now, I can explain why Professor Leonard Susskind has discussed classical field theory much more, but that would take more time. But let us understand that special theory of relativity is a field theory, and without the knowledge of classical field theory, you won't be able to understand that. So Professor Susskind makes it sure that you know what is classical field theory. This is a very good book. Teaching classical field theory, mathematics is fairly simple, and it deals with Maxwell's equations and field theory in details. Coming to the next most popular book would be this one, and I have given the description of the download link, which you can check in the description box. It is there in gutenberg.org. It is a very legal book, and you can very well download or read it online, which is written by none other than the propounder Albert Einstein, Relativity, the Special and the General. However, this book will also be a very good rigorous mathematical understanding by Farooq Rahman, the Special Theory of Relativity. You can go ahead and learn. This gives you a basic understanding of what are the best books, which book you should read, what is the mathematics. But there is I think there is a question that clicks on, or it is inkling in your mind, because special theory of relativity would lead to the next step. That is, can you learn general relativity without learning special theory of relativity? Well, most of the people would agree to that, and they would say, no, you need to learn special relativity to learn general relativity. But I would say yes, and I would like to prove my point. The reason is that if I take the basic elements of general theory of relativity, including Ricci curvature tensor, local and global structure, Schwarzschild metric curvature scalar, Ricci curvature tensor, parallel transport, Einstein field equations, and so on, you will see that all these actually consist more of the geometry rather than the mathematics. Those who are watching this video, if you have attended to my live webinar, which is almost over 2.5-3 hours on general theory of relativity, I have discussed a lot. So yes, this would require a different kind of an understanding of geometry. So if you have really no idea of special theory of relativity, just know the history, you can very well go into general theory of relativity. So the relativistic effects, that means when special relativity gets, I would say, generalized into general relativity, it tells about curvature of space-time. So there is a huge paradigm shift, and this shift is from relativity to geometry, from a change in mathematics and a change in our understanding of coordinate system. This has nothing to do with the Lorentz transformation, all those things. So although it would be, I would say, devilish step for you to take to jump into general relativity, I would say yes, you can very well learn. And also remember, general theory of relativity is more of a geometry rather than the relativity of simultaneity. So the left hand side are actually the basic mathematical elements and concepts of general relativity, like parallel transport, covariant derivative, geodesics. All of these are geometric understanding. All of these are understanding of curvatures. These are very more intuitive in nature, and it requires a lot of exotic mathematics that you need to know, including tensors. So giving you a very unusual understanding that yes, you can go into GR without STR, provided that you have a very good understanding of the non-Euclidean geometry. That gives us a complete understanding for you for special theory of relativity, and I'm immensely thankful for those who have watched this video. Please do subscribe and hit on the bell icon to get all the notification from Physics for Students. You can always write to me at this email ID, and don't forget to like to my other channel, General Relativity Explained, which is exclusive to General Theory of Relativity. You can also follow me on my Facebook, Instagram, and my LinkedIn and Twitter account. Thank you very much for watching this video. I will be back with more such surprising videos and interesting videos. But till now, from Physics for Students, may the good Lord be with you.